Hi, welcome back to Mrs. O'Graham's Maths. We are doing a worked solution walkthrough video for one of the D&D resource papers. So first of all, a big thank you to them for letting me use their resources in this way and make these walkthroughs for you. I have put a link to their website in the video description. And I strongly recommend that if you don't already have a paper copy of these, you go and order yourself one. They are excellent practice for the externals. And always worth trying to do it out on paper yourself before looking at what I do with it. Okay, so this one is for distributions. It's practice external assessment number 5 from their booklet. Okay, so on to question 1. We have the length of a human pregnancy being modelled by a normal distribution. Mean is 266, standard deviation is 16. We want what proportion of all human pregnancies could be expected to last less than 245 days or longer than 275. Okay, so we are looking for this to be, if we draw it out first, we've got normal distribution like so. The mean is 266. Sigma is equal to 16, and we want less than 245 or more than 275. So probability that x is less than 245 or more than 275 is equal to 1 minus the probability that it's in between those numbers. And that's what is easiest to do on the calculator. So we'll do 1 minus. We're going to our stats menu, distributions, normal, cumulative. The lower limit is 245. The upper limit is 275. Sigma is 16, and the mean is 266. So that is 0.6184. And if we do 1 minus, that is 0.3816. Now, what length of time marks the shortest 70% of all pregnancies? So we have the same mean of 266, sigma 16, and we're looking for the 70% that makes the shortest. So 70% here, what's that value of x? So for this, we have the probability that x is less than a certain point is equal to 0.7. For this, we use inverse normal because we're working backwards. We know the probability, we need the x. So we go distributions, normal, inverse normal on F3. We have our tail is on the left, the area is 0.7. Sigma and mean are still the same, so x is 274.4 days. Now we've got this histogram showing pregnancy length in days for a large number of human births over a period of time, and it's them being not induced means they were allowed to go to their natural length of pregnancy. The mean length of pregnancy for this data is 266, standard deviation 14.2. Okay, now, is a normal distribution appropriate model for these births? We need to justify our answer by describing features and then using at least one applicable calculation. So let's describe the features first. So we're looking at things like shape, spread, whether it looks like it's going to match the things we expect for a normal distribution. So I would say yes, it does look pretty much like a normal distribution, and we'll put some details of why. So yes, normal is a good fit. The first thing is the length of the birth is a continuous variable. The other thing is the picture of what it looks like is roughly close to bell-shaped and mostly symmetrical. An applicable calculation, so we pick a probability to try out. Let's say, for example, the chance of it being 280 or more. So the probability of x being greater than 280 on the histogram well, we have 11, we've got 7 and 1. So if we just go to add those up, we're going to have 19 there out of a total of, how many did we have? So we've got, oh, it doesn't tell us in the question, we'll need to add them all up. So that comes to 102 total, and we had 19 that were more than 280. So 19 out of 102 comes to 18.6%. Okay, now if we do x following a normal distribution with a mean of, what was it, 266, I think? Yes, we've got mean was 266, standard deviation 14.2. So that gives the probability that x is greater than 280 of, let's just go over to our calculator, distributions, normal, cumulative. Our lower limit is 280, upper limit something very large. The mean, sigma first is 14.2 and the mean is 266. That gives a percentage of 16.2, and these are quite close. And we know approximations aren't going to be perfect, they are an approximation, so this is close enough statistically thinking about this. Okay, part C, we've got hospital record time, the hospital records labour time for these normal births, which it assumes to be normally distributed. The probability from those records that a random woman's normal labour exceeds 12 hours is 0.233, and it being less than 10 hours is 0.652. From those two things, we need to determine the mean and standard deviation labour time. Right, so for this we don't know either the mean or the standard deviation. We're going to need to use simultaneous equations to get them. So those are the two things we're trying to work out. What we do know is that being more than 12 hours, so if we pop a 12 in there, that proportion will be 0.233. And less than 10, if we pop 10 in here, this proportion on all of this shaded bit here up to the 10 will be 0.652. Okay, now we need to use the Z curve to compare what happens on there and match it. So on the Z curve, to get a value in here that goes to 0.652, let's take off that mean line for a second. We'll just pop the mean there. For the Z curve, would have a mean of 0 and a standard deviation of 1. We want to know what goes on that number there to make that true. And we use inverse normal. So the probability that Z being less than a certain number has to equal 0.652. So back on our stats menu, go to distributions, normal, inverse normal. We've got a tail on the left, an area of 0.652. Sigma is 1, mean is 0, and that number that makes that happen is 0.3907. Then the next one is to look at what number will we get for Z to make that tail proportion 0.233. So the probability that Z is greater than a number has to equal 0.233. So this time we're looking for the tail on the right with an area of 0.233, same sigma and mean, and that is 0.7290. Okay, now we use that Z is equal to x minus the mean over sigma, and we match those two things up. So for the first one, where we had the area equal to 0.652. That happens when Z is 0.3907 and X is 10. And then for the other one, that happens when Z is 0.7290 and X is 12. So we're just popping that into there. Okay, now on this pink equation, we need to rearrange this into a format that we can easily pop into the calculator. So we'll go 0.3907, multiply it by sigma, add on mu is equal to 10. And then 0.7290 multiplied by sigma, add on mu is equal to 12. Now, equation solver. We are doing simultaneous equations. We've got two unknowns, both sigma and mu. We need to just double check we've written it in this form here. So something times the first variable plus something times the second variable is equal to a constant. Now we can pop in those coefficients. So we have 3.907. The coefficient for mu is 1, constant is 10. On the orange equation, we have 0.7290. Coefficient for mu is 1 and the constant is 12, and now F1 to solve. So remembering that the X was representing sigma for us here, so sigma is equal to 5.9119, or if we round that, it's just going to be 5.9, and the mean is 7.69 in hours. And there we go. Question 2 starts us off with a triangular distribution, and we're going to work out the probability that this random consultation will take between 20 and 30 minutes. Okay, so we have on our diagram here our mean height, sorry, not mean, mode height, and that's happening at 25. Now, I usually do these by similar triangles, just to mix it up a little bit for those that do like to use the formula on the formula sheet. I'm just going to do this one as that. Okay, so the height at 20, we use remembering that the formula on the formula sheet gives us this height. It doesn't give us the area or probability, it just gives us the height. So the height at 20, well, that's to the left of 25, so we use the formula that is 2x minus a over b minus a times by c minus a. Okay, now a is 10, so we can put a 10 in for all the places that we had an a. B is the end point, so that is 40. And C is our mode, which is 25. So we have, and X is, we were doing that at 20. So 2 times 20 minus 10, or 20 minus 10 is 10, times it by 2, we've got 20. On the bottom, 40 minus 10 is 30, 25 minus 10 is 15, so we have 30 times by 15, which is 450, so that comes to 2 over 45. We'll leave it as a fraction. I'm just going to move this up. I can see I haven't got a huge amount of space. We're going to do a similar thing, so at 30 minutes. So here is our 30-minute line. Now that's to the right of the mode, which means we need to use the one that goes 2 times b minus x, so 40 minus 30 over b minus a, so that's 40 minus 10. So we have 30 times by b minus c, so 40 minus 25 is 15. So that's also going to be 20 over 450, or 2 over 45. Now, on just going up to the diagram up here, we're trying to find the time in between these. So that bit there, it's going to be easier to find the time less than 20 and the time more than 30 and subtract that from 1. So that's what I'm going to do. So we will have the probability that x is between 20 and 30 will be 1 minus the probability that x is less than 20 minus the probability that x is more than 30. Right now, less than 20 is half the base times the height. So half the base, well, the base is 10 and the height is 2 over 45. More than 30 is half times the base, which again is 10, times the height, which is 2 over 45. So let's calculate those. Times 2 over 45. And we'll double that for the two of them. And we're going to do 1 minus that. So our final answer is 5/9. For part 2, we have a comparison. And this one has the probability of it being more than 28 minutes will be 35%. So we need to compare with Sally's obstetrician. So for Sally's, the probability that it'll be more than 28. Let's go back up to our diagram here. So we're going from 10 up to 40. I'll just redraw it actually, so it's easier to see what we're doing. 10 up to 40. The mode is at 25. We want the probability that it is greater than or equal to 28. To work that out, we do half times the base times the height. So the base is 40 minus 28 is going to be 12. And for the height, so our height of that, we'll use the formula on the formula sheet. So h is equal to 2 times 40 minus x, which is 28, over 40 minus 10 times 40 minus 25. So we're going to have 2 times 40 minus 28 divided by 40 minus 10 is 30 times by 40, that's a minus there, not a point. So 40 minus 25 is 15. So our height is 4 over 75. So we pop that into here. That times 12 and divided by 2 is 8 out of 25, or 0.32. So this other obstetrician's consultations are more likely to take longer because he's got a 35% chance of going more than 28 minutes, whereas Sally's has only got a 32%. Now for the new obstetrician, we need to work out their mode. So let's just fix that. There we go. They have a base that is the same. So it runs from 10 to 40. They've got a mode somewhere. We know that the mode has to be to the left of 28 because we know that at 28 we get this little triangle cut off where that area there is 0.35. Now we're trying to work out the mode on this one, which is C. Now we can work out what that height of that triangle needs to be, because half times the base times the height will equal 0.35. So half times the base, well, that distance from 28 to 40 is 12, times the height, if we call this little one there, that height h, is equal to 0.35. So 6h is 0.35, so 0.35 divided by 6 gives us that height is 7 over 120. Now, the formula sheet, we will use the formula 2b minus x is equal to b minus a, b minus c, would give us that height of 7 over 120 at x is 28. So let's pop in 28 for the x and pop in the b is 40. So we've got a 40 here and a 40 there. We've got a is 10, and from there we can work out c. So 40 minus 28 is 12. Times it by 2, we have 24. And then on the bottom here, we have 30 minus times by 40 minus c. Set that equal to 7 over 120. I'm running out of room a little bit, so I'm just going to move this over to here. Let's just pop that there. Okay. So now carrying on, I'm going to do 120 times by 24. And you can put this into equation solver if you prefer. 7 times 30 is 210 times by 40 minus c. So we've just cross multiplied there. 2880 divided by 210 is going to be that much. So 13.7 is equal to 40 minus c. So c is equal to 40 minus the 13.7. So c is 40, take away that answer, which is 26.2829 is the mode. Next, we've got 40% of the consultations from Sally's obstetrician are sent for a blood test. What distribution would best represent the probability of a patient having to go for a blood test? Okay, so we have a number of people that are seen by the obstetrician and a probability that they're sent for a test, so that fits a binomial. And we'll run through the FIST acronym of why that works. So binomial distribution with n number of patients and the chance of being sent for a blood test is 0.4. So starting with the F, we have a fixed number of patients. I for independent is that each patient's likelihood is independent of others. S for that probability of success stays constant at 0.4. And T, there are two outcomes, you need a test or not. Okay, so now if we have 10 consultations, what's the probability that in two successive days, 6 or more patients are sent for blood tests? So we have X is following a binomial distribution with 10 patients in a day, and the chance of them being sent is 0.4. On day 1, the probability that we have 6 or more is going to be X is greater than or equal to 6. Go to stats, distributions, binomial, cumulative. It's going to be 1 minus the probability that X is less than or equal to 5, because that's what our calculator can cope with. So that is 1 minus. Now I've reset the calculator since my last video, so we need to make sure that that data is being read from a variable, not a list. The X number is 5. Number of trials is 10. Probability of success is 0.4. So that chance is 0.8338. So 1 minus it will be 0.1662. Probability that X is greater than or 6 on 2 successive days. It's going to be day 1 would have that chance, and so would day 2. So we times them together. So we go over to 0.1662, and we got that squared is 0.0276. Okay, question 3. We've got this graph. It's about the people using the coffee vending machine in the waiting room. It was recorded every 30 minutes over a number of weeks, and the results plotted on this graph. So this is your chance of from 0 up to 6 people using the coffee machine within a 30-minute window. Now, we are being told about values of things within a time frame, so this is likely to be a Poisson distribution. Okay, the next bit asks us what's the best model to use in order to calculate the probability of n people using the coffee machine within this 30-minute period, and then justify your choice of that distribution along with the parameters. So a Poisson, oops, wrong pen. Let's go with a Poisson distribution. Because we have got that average number of things over a time interval. And we'll put in the justification. So we're using the acronym RIPS, so it occurs randomly. I is for independent, so the second bullet point, independently of each other. P is for proportional, so the rate at which it's used is proportional to the time interval we measure in. S for singly or not simultaneous, you can't have two people using the machine at the same time. Okay, so identify an assumption in part A that may be invalid. I'm going to go with the first one, that each person using the machine happens at random, because you could argue that it's a coffee machine. People are more likely to do that in the morning than the afternoon or at certain points in the day. So that's the one I'm going to use, and other possibilities are there. You could also argue a few other things. That could also come down to the rate at which the machine is being used might not be proportional as well, because different times of the day would have different things. And perhaps not independent either, because if you see somebody else getting up to use the coffee machine, it might trigger you to think, yeah, I want a coffee too. And I'm just skipping back up here because I realized I forgot something on the first part, which is that we needed to state the parameter. So justify the choice of distribution we did, but also calculate the parameter. Just a good example there that you need to go back and read the question and check that you've answered it before you move on. Okay, so we need to work out lambda on this one. So we have a 0 times, if I put the values on here, so we've got 0.13, 0.24, 0.22, 0.21, 0.12, 0.06, and 0.02. And for lambda, we do the value times its probability. I'm not going to bother putting in 0 times 0.13, it'll just be 0, but I will do 1 times 0.24. Then we're going to add 2 times 0.22, 3 times 0.21, 4 times 0.12, 5 times 0.06, 6 times 0.02, comes to 2.21. So lambda will equal 2.21 just there. Okay, now let's carry on. So now on part C, if lambda is equal to 2.21, the probabilities are marked on the graph now. We're going to do that. So that's what it's asking us to mark onto this graph here. So with a value of lambda being 2.21, we're going to pop that into a Poisson distribution. We want the values exactly at the point. So if x is 0 with lambda of 2.21, we've got a probability there of 0.1097. I'll just zoom in and do that a little bit more accurately. So just a little bit above the 0.10, we have 0.10, well, 110. Say 0.11. Okay, then coming out and doing it for x equals 1, we've got 0.24. So 0.24, that matches 0.24. For x equals 2, 0.27. It's going to be about here. x equals 3 is 0.197. 197 is about here. X is 4, 0.109. So 109 round about here, 0.11. And then for 5, 0.05. So 0.048. And 6, 0.02. Or 0.0178. Okay, so we've marked them on. Let's go back to the question. Discuss what conclusions you can draw comparing the model against what we had on the histogram, not histogram, bar chart. So looking back at it now, we can see that it's reasonably accurate for x equals 0, pretty accurate for, and reasonably accurate for x equals 3, very accurate for 1 and 6, mostly there, but perhaps a little undercooking it on 0, 3, 4, and 5, but not so accurate for x equals 2. And then at x equals 2, it's not a good fit. And there's a full write-up of how I've put those down. Okay, last little couple of bits here. So the office manager at the practice selected 8 30-minute periods at random and noticed that 2 of these showed no coffee sales. Choose an appropriate model, calculate the probability that half of these 8 30-minute periods could have no coffee sales. So using this observation from the office manager, we've got 2 out of 8 that didn't have any coffee sales. So the probability of no coffee sales is equal to a quarter. We've got n is equal to 8, and x is following a binomial distribution with 8 trials and probability of success is a quarter, where we're looking at success being that there were no coffee sales. So if that's true, in those 8, what's the probability that we get exactly half of them, so 4 of these times where there were no coffee sales? So we're using binomial distribution here, statistics menu, distributions, binomial. We want exactly equal to 4. We've got x is equal to 4, number of trials is 8, and the probability of no coffee sales was a quarter. So this gives us a chance of that happening as being 0.0865. And now we want to justify why we used binomial distribution. We've got a fixed number of trials. We're using the FIST acronym. Each trial is independent. The probability we can assume to be constant as what was observed of a quarter. And we can class it as 2 outcomes, either there were no coffees sold or there were some coffees sold. And that takes us to the end of this practice external assessment from the D&D Resources. If you found this helpful, please interact with the video in some way, like, subscribe, leave a comment. It's always nice to hear from people, but also if you found it helpful, other people probably will too, and your interaction with the video will help it make its way to other people that would be looking for this kind of stuff. Thanks for your support, and I will see you next time.